Welcome to this scientific lecture on one of the most fascinating and mysterious phenomena in physics, sonoluminescence. This is the emission of light from collapsing bubbles in a liquid driven by sound waves. So what exactly is sonoluminescence? Imagine you have a flask of water sitting in your laboratory. You apply ultrasonic sound waves to this water, and suddenly you see tiny flashes of light appearing inside the liquid. These flashes come from bubbles that are oscillating and collapsing due to the sound waves. Here's a visual representation. You have a flask of water, sound waves propagating through it, and tiny bubbles that emit light as they collapse. Sonoluminescence was first discovered in 1934 by scientists studying ultrasonic cavitation. But it wasn't until 1989 that single-bubble sonoluminescence was achieved, where one stable bubble could be trapped and made to emit light repeatedly. There are actually two types of sonoluminescence we need to distinguish. First is multi-bubble sonoluminescence, where you have many bubbles forming and collapsing chaotically throughout the liquid. This produces a distributed glow. Second is single-bubble sonoluminescence, where one bubble is stably trapped at a pressure node in the standing wave. This bubble oscillates and collapses rhythmically, emitting a flash of light with each collapse. This is what we'll focus on today. Let's understand the bubble dynamics. When you apply an acoustic field to water, you create regions of high and low pressure that oscillate in time. During the low pressure part of the acoustic cycle, the bubble expands to perhaps 10 times its minimum radius. The bubble grows slowly during this expansion phase. Then, during the high pressure part of the cycle, the bubble collapses violently. The collapse happens extremely rapidly, in just a few nanoseconds. It's during this violent collapse that the light is emitted. Let me ask you a question. Why does the bubble emit light when it collapses? The answer lies in extreme compression. When the bubble collapses, the gas inside gets compressed to an enormous degree. This compression happens so rapidly that there's no time for heat to escape. We call this an adiabatic compression. Let's talk about just how extreme this compression is. The numbers are truly staggering. The maximum radius to minimum radius ratio can be about 10 to 1. But remember, volume scales as radius cubed. Volume is proportional to radius cubed. So if the radius changes by a factor of 10, the volume changes by 10 cubed, which is 1,000. The bubble is compressed by a factor of about 1,000. For an adiabatic process, we have pressure times volume to the power gamma equals a constant, where gamma is the heat capacity ratio. This is the adiabatic equation. For air or similar gases, gamma is approximately 1.4. The pressure ratio equals the inverse volume ratio to the power gamma. 1,000 to the power 1.4 is approximately 15,800. The pressure increases by nearly 16,000 times. That's an absolutely enormous pressure increase. We're talking about pressures reaching thousands of atmospheres inside a bubble that's smaller than a grain of sand. Now let's estimate the temperature inside the collapsing bubble. This is where things get really interesting. For an adiabatic process, temperature times volume to the power gamma minus 1 equals a constant. This is the temperature-volume relation for adiabatic compression. Temperature final over temperature initial equals the inverse volume ratio to the power gamma minus 1. Let's start with room temperature, about 300 Kelvin. 1,000 to the power 0.4 is about 15.8. This gives a final temperature of about 4,700 Kelvin. But wait, this is just a basic estimate assuming ideal gas behavior. Real measurements and more sophisticated models suggest temperatures could be much higher. Experimental evidence suggests the temperatures inside these collapsing bubbles are far more extreme than our simple calculation suggests. Analysis of the emitted light spectrum suggests temperatures between 10,000 and 25,000 Kelvin. That's hotter than the surface of the sun, which is about 5,700 Kelvin. Some theoretical models even predict core temperatures exceeding 100,000 Kelvin. At these temperatures, you start to see partial ionization of the gas, creating a small plasma inside the bubble. Picture this, a tiny region smaller than the width of a human hair, reaching temperatures comparable to stellar interiors, surrounded by liquid water at room temperature. The temperature gradient is absolutely enormous. Let me ask another question. What creates the light? What is the actual mechanism? And here's where sonoluminescence becomes truly mysterious. The answer is We don't fully know. There are competing models, and the phenomenon is still not completely understood despite decades of research. Let me explain the main competing models for how the light is produced. The first model is thermal Bremsstrahlung radiation, also called free emission. In this model, the gas inside the bubble is heated to such high temperatures that it becomes partially ionized, forming a plasma. Free electrons scatter off ions, and during these collisions, they emit photons. An electron approaches an ion, gets deflected by the electric field, and emits a photon in the process. This is Bremsstrahlung radiation. This model predicts a broad spectrum of light, which is consistent with observations. The spectrum should follow a thermal distribution. The second model involves collision-induced emission from neutral molecules. In this model, neutral molecules collide with each other at very high speeds due to the extreme temperatures. During the collision, they briefly form an excited complex that then emits light. This mechanism is particularly important when the bubble contains noble gases like argon, which don't ionize as easily as molecular gases. The third model proposes that the light comes from shockwave heating. As the bubble wall collapses inward, it moves faster than the speed of sound in the gas. This creates an inward-moving shockwave that focuses at the center. The shockwave converges at the center, creating an extremely hot spot that emits light. This is similar to what happens in inertial confinement fusion experiments. Some calculations suggest that the shockwave can create local hotspots exceeding 1 million Kelvin for brief instants. At these temperatures, you might even see nuclear reactions, though this is highly controversial. There's even a more exotic model, quantum vacuum radiation, proposed by Julian Schwinger. This model suggests that the extreme electric fields and rapid changes during collapse might polarize the quantum vacuum itself, causing it to emit photons. This model is highly speculative and not widely accepted. It would require conditions even more extreme than currently believed to exist in the bubble. So why, after decades of research, do we still not have a complete understanding of sonoluminescence? First, the phenomenon involves extreme spatial and temporal scales. The light is emitted from a region smaller than a micrometer, over timescales of picoseconds or less. It's incredibly difficult to probe experimentally. The size is less than 1 micrometer. The flash duration is less than 1 nanosecond. Second, it's a complex multiphysics problem. You have to couple together hydrodynamics, thermodynamics, chemistry, plasma physics, and radiative transfer, all happening simultaneously and nonlinearly. Third, the boundary conditions are difficult to model accurately. The interface between the hot gas and cold liquid is moving at supersonic speeds and is unstable. Fourth, the observed spectrum doesn't perfectly match any single model. It shows features that could be consistent with multiple mechanisms operating simultaneously. The spectrum is a broad continuum, spanning from ultraviolet to infrared, with no sharp features that would definitively point to one mechanism. What are researchers doing now to understand sonoluminescence better? One approach is using noble gases, like argon or xenon. These simplify the chemistry because noble gases don't form molecules, making it easier to isolate physical effects. Researchers are using advanced high-speed imaging and time-resolved spectroscopy to probe the bubble dynamics and light emission with unprecedented detail. Computational simulations are becoming more sophisticated, incorporating better equations of state, transport properties, and radiation physics. Some researchers are looking for trace fusion products, like neutrons or helium-3, which would indicate if temperatures are reaching nuclear fusion thresholds. This is extremely controversial. Let me give you an analogy to help understand why this is so difficult to study. Imagine trying to study a car crash that happens in 1 nanosecond, where the cars are smaller than a grain of sand, and you can only observe the light emitted during the crash. You can't put sensors inside the cars because they're too small. You can only observe from outside and try to infer what happened from the light and sound produced. That's essentially what we're doing with sonoluminescence. We're trying to reconstruct the physics of an incredibly violent, incredibly small, incredibly fast event from indirect observations. You might wonder, does sonoluminescence have any practical applications? The extreme conditions might be useful for chemical synthesis, creating compounds that are difficult to make by other methods. It's also being explored for ultrasonic cleaning applications. It provides a tabletop way to study extreme states of matter that normally require large facilities. This helps us understand astrophysical phenomena. Understanding sonoluminescence helps us understand cavitation damage in pumps, propellers, and medical ultrasound devices. Let me summarize the key points we've covered. Sonoluminescence is the emission of light from bubbles that collapse violently due to acoustic pressure oscillations. The compression is extreme. Volume reduces by a factor of about 1,000, and pressure increases by about 16,000 times. Temperatures inside the bubble likely reach 10,000 to 100,000 Kelvin, possibly even higher in localized regions. There are multiple competing models for the light source: thermal Bremsstrahlung, collision-induced emission, shockwave heating, and even quantum vacuum effects. The phenomenon remains not fully understood due to the extreme spatial and temporal scales involved and the complex multiphysics nature of the problem. Sonoluminescence represents a remarkable window into extreme physics. It shows us that even in a simple glass of water in a laboratory, we can create conditions that rival those in stellar cores, and that there are still fundamental mysteries in nature waiting to be understood. The fact that we can't yet fully explain something so seemingly simple reminds us of the beauty and complexity of the physical world, and the importance of continued scientific inquiry.